Okay, hello everyone. Okay, alright. Ugh, tired. Okay, so I'm going to show you how we calculate the heat of reaction for different types of reaction. Okay, so in total, you are learning 4 different types of heat of reaction: heat of precipitation, displacement, neutralization, and combustion. Okay, so you need to know how to calculate the heat of reaction for 4 different types of reaction. Alright, now the definition is given in your textbook or in your what you call reference book, but the thing is when they ask for the definition, right, you need to change the definition accordingly. So I show you one example. Okay, heat of precipitation. Okay, the general definition here is like this: heat change when 1 mole of precipitate is formed from its ions in aqueous solution, right? This is a general one, but if you want to write it in a specific way or in your questions, right? Okay, so this is how we do it. So they give me the thermochemical equation, and then remember this is a negative sign, so this is exothermic reaction. Okay, and then okay, very nice, they give me the ionic equation. So the definition for this heat of precipitation is heat change, right? Meaning we need to mention 50.4 kilojoules of heat energy is released, okay, when 1 mole of that 2 ions, okay, I use the ionic equation here, reacted with 1 mole of sulfate ions to form 1 mole of lead 2 sulfate. Alright, meaning this one. 1 mole of precipitate, meaning you need to give the name of the precipitate accurately. Alright, lead 2 sulfate. Okay, so we need to change the definition according to the question. You cannot just write this general one. If you write this general one, you won't get marks. Okay, and then let's just revise back a bit. Energy level diagram. So I just draw lah for you guys. Energy. Okay, and then the equation, since I have the ionic equation, then I use the ionic equation. 2 plus, and so for 2 minus, this is PbSO 4. And then don't forget, we need to put in the heat of reaction, which is this one. 4 kilojoules per mole. Okay, so that is a example. Alright, show you another one. Key heat of displacement. Okay, if you look at the general equation here, heat change when 1 mole of metal is displaced. Okay, you can only use this word, don't use other word. Don't use replace. This is the key word, displace. Don't change the word. From its solution by a more electropositive metal. So how we change it according to the question is heat change, meaning heat release, is release. How I know is release is because of the sign here. Is release when 1 mole of, okay, so you need to know who is being displaced. So if you remember your electrochemical series, the one that is more electropositive or the one that is higher will displace, meaning the one higher will kick the lower out. So zinc will go and kick the copper come out. Alright, so when 1 mole of copper is displaced from the solution, meaning the name, copper 2 sulfate solution, by a more electropositive metal, meaning by who? By zinc. So you need to give specifically. Alright, that is how you should write your definition. Okay, a lot of students, they always give the general one without taking into consideration the question. Okay, show you another one lah. And then if here you know the ionic equation, then you write the ionic equation lah. Alright, for those who already forgot how to write your ionic equation. Okay, metal cannot dissolve, so metal remain a metal. Sulfate, you need to know the type of salts that dissolve in water. Okay, sulfate salts, copper is soluble, so we separate. Alright, zinc sulfate is soluble, so we separate. Okay, just a little bit of revision on how to write your ionic equation. This is solid, meaning metal. Metal will always remain as metal. Alright, and then the same ions on the left and right, we cut off this and this. So your ionic equation here is zinc plus copper ions. Zinc ions plus copper. So I put this on top here. Reactant. product, heat of reaction, -217 kilojoules per mole. So again, check labeling, product, reactant, reactant, product got, this one got, arrow got. Okay, so that is it. Alright. Okay, if heat of neutralization, okay, 57 kilojoules of heat energy is released when 1 mole of water is from the neutralization of, okay, what acid and what alkali you need to mention. Okay, nitric acid with potassium hydroxide. Okay, so I'm just showing you how you should write your definition. Alright. Okay, if it's combustion, heat energy is released. Okay, when 1 mole of fuel, right? Fuel here meaning is this one. So you need to know your carbon compounds, division of your carbon compound. So functional group here is OH. So this is an alcohol. So 2 carbon alcohol is ethanol. Alright, it's burned completely in excess oxygen. You must put the word excess in. Okay, alright, so the 4 different types of heat of reaction. Now, of all the 4 reactions here, right, only the first 3 got ionic equation. Combustion don't have ionic equation. So, don't have ionic equation, I just use this one for my energy profile diagram. Okay, so that is it. Okay, the 4 different types of reaction. Alright, so I'm going to show you how we calculate the heat of different reactions, the heat of reaction for different reactions. Okay, first I'm going to show you the step-by-step calculation here, and then I'm going to show you different examples, alright, so that you can understand it more familiar. Alright, to calculate the heat of reaction, our formula here is this one. Heat of reaction is equals to heat energy divided by number of mole. Okay, number of mole, this is number of mole. Alright, so H is your heat energy. Okay, so heat energy, if you learn in physics, we are using MC theta, the one in your heat. Alright, this one is number of mole. Okay, so in order to calculate the heat of reaction, I need these 2 things. The heat energy released or absorbed, and the number of moles of the compound or substance that it's formed. Alright, so first thing, to use MC theta, I need to know the mass, right? They will give you this one. 1 gram equals to 1 cm cube. Meaning that every cm cube is equals to 1 gram. So to calculate the mass, very simple. Just look at the volume. You add up the volume to calculate mass. Alright, so this is 120 grams. Okay, temperature change. Because theta, I need the temperature change. So average temperature, so 32. Okay, if you see here, 32, 29. So you minus off. So you get 3 degrees Celsius. And then you jump out inside the MC theta. Alright, specific heat capacity given is this one. So we use their value lah. Okay, so 120 grams times 4.2 times 3. So you will get your heat of reaction. Okay, 1512, not heat of reaction, the heat energy. Kilojoules, joules. Okay, here we don't need to put the sign because this is the heat energy release. Okay, only the final answer, the heat of reaction, then only we put the sign. Alright, determine the number of mole. Because I want to calculate heat of reaction, I need the number of mole. Okay, this one a little bit 麻烦. 麻烦 in Mandarin meaning it's very troublesome lah. Alright, number of moles of blah, 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 blah. So technically you just calculate the number of moles of the both ions here. You have the same volume and the concentration, right? So use MV over 1000. So 60 times 0.25 divided by 1000. Okay. So 0.015 mole. Okay. Same thing goes to your bromide. Alright, then we need to write this. We always need to write this from the equation. Okay, for heat of precipitation, how we normally write this is 1 mole of silver ions react with mole of bromide, super duper long, to produce 1 mole of silver bromide. Okay, so this one is based on the equation here, right? Your balance equation here. Okay, therefore 0.015 mole this is a label of work. Oh my god, oh my god. I wonder who is the first person who asked everyone to write all these things. So curious, man. Okay, done. Alright, so why I need to know the mole of silver bromide? Because this is to calculate the heat of reaction, right? So if the question gives you like this, heat of reaction, you need to know what kind of reaction is this. Okay, now if you still remember your salt chapter in your form 4, 2 soluble salts you combine to get 1 insoluble salt, meaning that this is your double decomposition reaction. So the heat of reaction that you're calculating here is the heat of precipitation, meaning that I want to know who is the one precipitating. Okay, that is why I'm calculating the number of mole for AgBr. Heat of precipitation, meaning I need to calculate the heat energy released when this fella precipitates. Okay, this fella here that makes our life miserable. Yeah, this fella silver bromide. Right, so I hope you roughly understand. Okay, later I'll show you a few more examples. Okay, so now we have the heat energy release, which is 1512. Right, we jump out into the equation 1512 divided by number of mole of AgBr. 5, so we are going to get 512 divided by 0.015. Okay. If you use a calculator and calculate, you get 100,000. So I'm going to convert into kilojoules. So 100.8 kilojoules per mole. Okay, your unit is kilojoules per mole. Don't forget to add the sign at the front. Since this is an exothermic reaction, how I know exothermic? Because temperature increase. Alright, meaning here I must put the sign. If it's endo, also you must put the positive sign. Okay, don't forget that. Alright, then we draw the energy level diagram. Exothermic, so going down. Just quickly draw for you. So this one just now is Eg and Br negative. This one we get AgBr. Heat of reaction calculated is this one. Alright, so let me check. The group, term product, heat of reaction, arrow. Okay, done. Okay, so that is how you calculate. Alright. Okay, so let's try a few more questions. I'll show you a few more so to help you understand more. Okay, so excess zinc powder is added into copper sulfate solution. Calculate the heat of displacement of copper. Alright, heat of displacement. Okay, so again, I'm using this formula, right? Okay, before that, we write the equation first. Okay, zinc powder react with copper sulfate. Okay, remember zinc goes in, copper come out. So you get zinc sulfate and copper. Alright, so I want to calculate the heat of displacement. So heat of displacement meaning H over X, right? If you want to calculate separately also can lah. Or sometimes because I didn't know this is MC theta, right, then I can also put in like this. MC theta. Also can. Okay, you can straight away put the formula here to calculate, also can, no problem. But maybe you will like it better if we calculate separately. Right, let's calculate the heat energy release first. Okay, how do I know it's heat energy release? Because this word temperature of the reaction increases. So I know it's exothermic reaction. So let's calculate H, the heat energy release, MC theta. Okay, mass, remember we look at the volume. We look at the volume. So 50 ml, no other, right? So this is 50 grams times 4.2 times temperature change. This one already tell me increase by 5 degrees Celsius, meaning this is my temperature change. Alright, so you get 1050 joules. Okay, now to calculate the number of moles. Alright, so first thing we calculate number of. Okay, based on the question, I can only calculate the number of moles of copper sulfate because they only give me this information, the volume and the concentration. Okay, so meaning I can only calculate this one. I need to calculate this one first. Alright, so 50 times 0 0.1, 1000. Okay, so this is, 0.005 mole. Alright, now once I know the number of moles of my copper sulfate, okay, I need to know who is being displaced. Question already tell me heat of displacement of copper. I want to know copper's number of mole. So based on the equation, okay, we always need to write this. Very troublesome. Okay, so based on the equation here, 1 mole of copper sulfate is equivalent to 1 mole of copper. Alright, meaning the mole that you calculated and the mole of what they want. Okay, heat of displacement of copper. So if this one is 0.005 mole, I'll write faster a bit lah, 0.005 mole copper. Okay, so now I have the number of mole of copper. I have the heat energy released when the copper is displaced. I can calculate the heat of reaction. So heat of reaction equals to, this one how much? 1050 divided by 0.005 mole. Okay, so the heat energy release is 210. I change to kilojoules. Kilojoules per mole. Okay, exothermic, negative sign in front. So that is how you calculate your heat of reaction. Ooh. Okay, alright. Let me show you another. Let me show you the second one. Okay, this one, right? They already give me the heat of reaction. Okay, calculate the heat release. You must know the difference between heat of reaction and heat release. Okay, heat release meaning I only want to know H is how much, not delta H. Delta H is heat of reaction. Okay, calculate heat release meaning I want to know MC theta is how much. Basically, is that one. Alright, heat release. So since they already give me this one, right? It's based on my formula here. Delta H equals to heat release divided by number of mole. I want to know what is this. So I need to know the number of mole. So already given here. So we just calculate lah. Number of moles of who? Copper sulfate. 50 times 1 divide 1000. MV over 1000 lah. So 5 mole. Okay, and then always need to write this based on the equation. Okay, what we calculated is copper sulfate. Okay, who is displaced? Right, you need to know is what reaction. Just based on the chemical equation, you must know is what reaction. So this is a displacement reaction. So the one that is being displaced is the copper, right? So meaning you take the ratio between what you calculated and who is displaced, meaning copper. So therefore, if this one is 0.05 mole, this is also 0.05 mole of copper. So now I have the mole of copper I can put inside here. So heat of reaction already given. Okay, when we calculate for the heat energy release, right, you don't need to put the negative sign in. So we just jump out in 210 kilojoule. If you want to change to joules also can. Okay, heat and then 0.05. So heat energy release is 10500 joules or 10.5 kilojoules. Okay, that is how you calculate heat released. Right, one more. Okay, magnesium powder and iron sulfate. Again, this is a displacement reaction. Okay, calculate increase in temperature, meaning they want to calculate the theta value. Alright, so how we calculate? So I have the heat of reaction, let me see. Heat of reaction given is this one. Alright, okay, we calculate number of mole first. Of who? I can only calculate the number of moles of iron 2 sulfate, FeSO4. So meaning 80 times 0.4 concentration 1000. So if you calculate the number of moles for your iron sulfate, okay, 0.4. Okay, the number of moles that we get here is this one, 0.032 mole. Alright, then we need to use this. Based on the equation, alright, the one that we calculated, which is iron sulfate, and the one that is being displaced. So you need to know who is being displaced. So magnesium goes in, iron comes out. Alright, so 1 mole of iron. Okay, meaning that for every 1 mole of iron that comes out, the heat energy that you are releasing is 189 kilojoules. Every 1 mole iron come out, 189 kilojoules heat energy released. That is the meaning of this equation here. Okay, therefore this one 0.032 mole also equivalent to this one. We take the ratio. Alright, so now I have the number of mole of iron, I have the heat of reaction. So I'm going to jump into this equation here. Okay, now to calculate the increase in temperature, your heat of reaction you must change back to joules. If not, you will get a very small decimal value. Alright, heat of reaction over number of mole is 0.032. Okay, so 18900 times 0.032. This is, so the heat energy release is, write it in this way, 6048 equals to H. And then your heat energy release, the formula is mc theta, right? So equals to mc theta. So mass, we look at the volume, which is 80. 4.2, temperature change, I don't know. So we just divide. Okay, 6048 divided by 80 times 4.2. And then you will get your temperature is 18 degrees Celsius. Okay, that is how you calculate. Alright. If you don't want to do it like this, meaning if in this step you want to straight away change into mc theta, also okay. So it becomes like this lah. 80 times 4.2 theta 0.032. Also can. Alright, so it depends on how you calculate that, just as long as you calculate correctly. Alright, meaning at this part I straight away apply this into this formula here. Okay, this one I do it step by step, one by one. I calculate this one, then only I change into this one. Okay, but the main idea is when you calculate the increase in temperature, your heat of reaction must convert back to joules. If you never convert back to joules, right, this one will become 0 point something degrees Celsius. So it's not logic, right? Because your temperature change must be, what they call, must be high. It cannot be 0 point something temperature change. Okay, especially since you have a large amount of energy is released. Okay, so basically that is it lah. Alright, calculations involving heat of reactions. Okay, so you can use the same exact method to solve all your different what they call calculations. All right, you just need to identify is what type of reaction, and then who is involving who and who lah. Okay, so I hope this one will help you all to roughly understand how to calculate the heat of reaction. Okay, all right, so that is it. Okay, I hope this one can help you guys. If you have anything you don't understand, all right, if you want me to clarify some more, you just let me know. All right, I will try my best. Okay, all right, bye everyone, good luck in your trials.